Hello, AP Chemsters. This is Mrs. Vandewalle bringing another edition of the Blank Wall video series. We're going to continue on our discussion of kinetics. Again, we're going to start with section 12.6, and if you're wondering where section 12.5 is, it's actually found in problem 16. It's a summary of the integrated rate laws there. So anyway, section 12.6 is reaction mechanisms. This is how the reaction takes place. A lot of you think that if you write down a balanced equation, the reactants automatically become products. And you don't think about how they actually become products. I have been told, although I don't know for certain, that every time you take a deep breath in and you breathe in that oxygen, and by the time you exhale again, the oxygen has been somehow magically converted into carbon dioxide. I've been told that it takes 22 chemical reactions for that to happen. Obviously, it has to happen awfully quickly or it wouldn't work. So anyway, how does the reactants actually become products? That's what the mechanism is actually all about. So the mechanism is a series of elementary steps that must satisfy two requirements. The first one, the sum of the elementary steps must give the overall balance equation for the reaction. That is just like Hess's law. You're going to cancel out things that are both reactants and products in different steps, and when you're all done, it must agree with the overall balance equation. That's fairly straightforward. Number two is really going to be the new material. The mechanism, the series of steps, must agree with the experimentally determined rate law. Just like what we did in the Crystal Violet lab, that you did the experiment, you found the data, you used the integrated rate law to determine is it a zero order, one order, or a second order. And so by determining the order, that it should correspond with the mechanism. So you will know that if your series of elementary steps are actually correct by how it relates to your determined rate law. So there's a couple definitions we need. What's an intermediate? First of all, I kind of referred to that earlier. An intermediate is a species that is neither a reactant nor a product, but is formed and consumed during a chemical reaction. So it doesn't show up in your balanced equation, but it's part of the whole process. Finally, what's an elementary step? It's a reaction whose rate law can be written from their molecularity, which is the balance equation for the step. So here's problem number 16. It says define the terms elementary step, reaction mechanism, intermediates, and rate determining step using the following example. So it says the rate laws first will determine that the rate is equal to a constant times nitrogen dioxide to the second order. And here's a couple steps that someone proposed. This is what we think is going on here. And underneath the line is the proposed balance equation. We think this is what's happening to make nitrogen dioxide and carbon monoxide to yield nitrogen monoxide and carbon dioxide. So what's the elementary step? Each of these equations are. So those are your two elementary steps. The reaction mechanism, again, is the series, is the total number of steps that it's going to take to give you the overall balance equation. So it's really the sum of elementary step 1 and elementary step number 2. That would be the reaction mechanism to get us our final balanced equation. The intermediate, well, if you look back at the definition, what is the intermediate? It is what is produced and consumed in these elementary steps. If you look over here, what is produced in the first equation? You have NO3 plus NO. Well, what's the reactant in elementary step number 2? It's NO3 and CO. So obviously, it's what you cancel out here. And notice the intermediate does not show up in the balanced equation. So finally, what is the rate determining step of the following example? What exactly does that mean? Well, which step, elementary step number 1 or number 2, is going to determine the overall rate for the entire process? And if you think about it, it's going to be the slowest step. Now, I was thinking about this during our last fire drill. This is kind of a bad example. I'm always thinking of chemistry, you know me. And so when we were leaving the building, we're all leaving pretty quickly. And next thing you know, all these kids are bunched up at the staircase. And, you know, that is the slowest step to get us up into the parking lot. So in a sense, how fast people are going up through the staircase to get the parking lot is the rate determining step. It's our slowest step. So however fast people can go up the steps is how fast people are going to end up in the parking lot. Here's another kind of a goofy example. Be of like, say you have a big dinner, big family over, and all the ladies clear the table. Now we're going to wash the dishes and put the dishes away. But my grandma is wiping the dishes. So guess what? The table gets cleared right away. I'm washing dishes and I'm pretty fast here. And they all pile up on the drainer because grandma is still wiping the dishes. So how fast can all those dishes be put away? How fast my grandma can wipe the dishes. So anyway, what's going on here? So our slowest step is our rate determining step. So there is a relationship between the given rate, where it says rate equals K times NO2 squared, and the slowest step. That is your rate determining step. So we need to look at these different steps. So look at step number 1. I'm going to write down here. So in a sense, I wrote down the rate for each equation. And look at the rate number 1. Wow, that looks an awful lot like our overall experimental rate, which is K times NO2 squared. And so the rate of the elementary step, number 1, matches the overall rate. So what does that tell me? That is probably my slow step. It's probably the one that's going to determine the overall rate of the overall equation. Now, does rate 2 have anything to do with the overall determined rate? Not at all. You don't see NO2 or CO in the rate equation at the top there. So my rate determining step is from the step number 1, where the 2 nitrogen dioxides make nitrogen trioxide and nitrogen monoxide. Now there's another term that we need to look at. I've already mentioned it once, and that is called molecularity, and that is the number of species that must collide to produce the reaction indicated by that step. So actually I kind of want to change these definitions a little bit, tweak them if you will. So what is a unimolecular step? Well, uni obviously means one, so it's a reaction that involves one molecule. I want to change that last part. It's not just one molecule, it's one reactant molecule. So can you make that change for me? So obviously a bimolecular step, bi meaning 2 molecules, is a reaction involving the collisions of not just 2 species, but of 2 reactant molecules. And then obviously the termolecular step is a reaction involving the collisions of 3 species. Well, cross out the word species and write 3 reactant molecules. And so this table 12.7 kind of summarizes these elementary steps. So there is a relationship between the molecularity of the elementary step and the rate loss. So if it's a unimolecular step, the rate loss to the first order. If it's a bimolecular step, then the rate is to the second order. Now notice, you can have 2 of the same reactants colliding to get a second order, or you can have 2 different reactants colliding and still go to bimolecular, and it's still an overall order of 2. So A to the first, B to the first is an overall rate of 2. A termolecular step is actually quite rare. It is very, very difficult to get 3 molecules to collide at the exact same time with the exact same orientation with the exact amount or more speed or energy. and you really don't see this term molecular steps. It can happen, but don't expect it too often. Sorry about that. Trying to turn the page here. All right. So again, the rate determining step is the reaction that determines the rate of the reaction. So going back to the example we just gave you, the overall reaction is given. The rate determining step is given. There are your two elementary steps. And then again, this is summarizing which step is rate determining. If it's step number 1, we're looking at the rate of the first one. It does agree with the experimental results, and step number 2 definitely does not. So for problem number 17, for elementary steps, what can the coefficients be used for? I don't know if you remember that chem activity we did earlier, and they had a big chart on it saying, so can you use your coefficients as exponents? And the answer was, well, no. It seemed to work some of the time, but not all the time. And so what's going on here? Is there a certain kind of relationship between the elementary steps and their coefficients? Well, let me give you a couple examples for you. Okay, so maybe we can answer the question then. So again, an elementary reaction, what the question is asking for is that these will occur in one step. So here's perhaps one step. Okay, so we need reactant A, reactant B making some kind of a product. So here's my A and here's my B. So they're going to come together and they're going to collide and they're going to make C here. Now remember what we talked about earlier? What if we doubled the amount of B? So we have twice the concentration of B than we have, in the first experiment. So listen to this logic. If you double the amount of B, then you have twice as many B molecules, so the reaction is going to speed up by 2. So if that's the case, if you double the B, you're going to double the reaction. Well, that should sound awfully familiar because that means that the rate is going to be first order. Okay, and the same logic will apply with A. If you double the amount of A, you're going to double the rate at which the reaction is going to occur. So again, it's a first order. So watch this. So if you apply that logic, if you double the B, you're going to make it go twice as fast. If you double the A, it's going to go twice as fast. So wow, it is the same order in which the coefficients occur. Now let's try another example here. All right, so what if I have another reaction where I have 2 B molecules, okay, and they're going to collide and make product C. And so what happens here? Listen to this logic. If we double the amount of B, the reaction will speed up now by a factor of 4. Does that sound familiar? Since twice as many molecules are now involved. And so they are colliding and they are going on. Hang on. All right, sorry about that, my phone rang. So anyway, we're back to this case again. So if we double the amount of B in the same space, the reaction will speed up by a factor of 4, since twice as many molecules are involved. So if you imagine what's going on here, because if I have twice as many molecules and I'm working with the exact same molecule and they're going to be colliding a lot more now because you have more molecules, you're going to end up quadrupling the rate at which it occurs. So hopefully that relationship sounds familiar. If I doubled B and the rate quadrupled, it's going to be second order. So here we go. So there the coefficient does have to play with, or does have a relationship with the rate. And that is typically how it works with these mechanisms. We'll save the next couple questions or problems to do in class together. Hope you have a great day.